Let's continue with thinking about D and its properties. This is going to sync up a little bit weirdly with the previous video because in the interim I was working with my class on some stuff, but it should make sense, even to the YouTube community. We did in class kind of an investigation version of what I did in the previous video, and in particular the key thing was that if you have f times dx, we thought it was a pretty reasonable rule to just say, let's take df and then wedge that with dx. One thing that I haven't mentioned yet is that when we have a function times any kind of form, remember a function can be considered a zero form, and we're actually just going to say that if we want consistency in notation, we could declare that a zero form wedged with a one form is just what we've always been doing, of multiplying the form by the function, which just basically scales it. Remember with the picture of sheets, the stacks and everything, it just makes the stacks closer or together farther apart. So we could really write it this way, in which case it looks a little bit more reasonable. That dx is a constant and it's kind of being pulled out. It's really important that it's pulled out on the right because order matters all the time with the wedge product. So that was our motivation. Let's just declare that to be a rule. Well, this isn't really fully expanded out yet, though. df, we know that d of a function is basically like the gradient. It has a formula in terms of partials of f. So let's just go ahead and jump all the way to a general one form, and we'll get the formula for d of a general one form just from linearity. We're going to assume or essentially define that d is linear, so the sum distributes over the sums, and then we're going to use this rule and the rule for functions. So we get dp wedge dx, dq wedge dy, dr wedge dz. So we're going to expand out dp in terms of derivatives. So I'm using the compact notation for derivatives. This is partial p, partial x here. And then so I'm just expanding out the dp, dq, and dr. And then some stuff just dies, like dx wedge dx dies, dy wedge dy, dz wedge dz. So we don't get 9 terms when we distribute this out. We get only 6. And then we get things like py dy wedge dx. Well, that's not the order we've been traditionally writing things in for two forms. We want to write them in cyclic order. So that's going to be a minus py dx wedge dy. Is there anything else with dx wedge dy? You bet. Q sub x dx wedge dy, and that's written in the right order already, so we get it with a plus sign. Now, if you just pause it and run through the rest of it, you're going to see that we get 2 things attached to dy wedge dz, 2 things attached to dz wedge dx, etc. And these guys should look awfully familiar. These combinations of partials, if these had been the components of a vector field, if it was pi plus qj plus rk, these would be exactly the components of the curl. And that makes sense because we've actually seen when we talk about flux integrals how there's this correspondence, a different correspondence between vector fields in two forms that seems to put the p here, the q here, and the r here. So let's formally really define that. These notations are somewhat idiosyncratic. A lot of people sort of try to avoid coming up with these notations. I don't know if there's really an official standard. I don't think there is. But here's some decent notations for it. So we start with a vector field, and we can either turn that into a 1 form or a 2 form. And it really depends on what we're going to do with it. We turn it into a 1 form if the purpose is a line integral. If what we were going to do that is line integral, like work, for example. We turn it into a 2 form if our purpose is a flux integral. So this is one of the really essential insights of the form perspective, is that when we were thinking about integrating vector fields over curves versus integrating vector fields over surfaces, the reason it wasn't that the process that we thought we had was different. Calculations seemed very different. And that really was because we weren't integrating the same kind of object. And this is making that explicit. To integrate a vector field over a curve, you actually first turn it into a differential form using this prescription, a 1 form, and then integrate that 1 form over a curve, which is how things are supposed to go. Or you use this prescription. We're going to call that f star instead of f tilde. We put p in front of dy wedge dz, q in front of dz wedge dx, that's cyclic order, r in front of dx wedge dy, and then we integrate that over a surface. And that's matching up correctly, that 2 forms should integrate over surfaces, 1 form should integrate over curves. And so from this perspective, it was just bizarre that we were trying to integrate the same, we were pretending to integrate the same object, a vector field, over 2 objects of different dimension. And now we're never going to do that again if we stay in this form perspective. Okay, so just to make official the kinds of things we've seen about D here and using this new notation, fill in the blanks where f is a function and big F is a vector field. Okay, so df, we've been doing that for a while now in these videos. And remember, what we've been saying all along is it's an analog of the gradient. Okay, well, this is a way to make that precise. If you take, if you go in here and you put in grad f, that's going to be f sub xi plus f sub yj plus f sub zk. You turn that into a one form by this prescription, you're going to get the formula for df. So this is a precise way to say, using this notation, that df is the one form version of the gradient. Okay. Now what about if you do a vector field? We take a vector field. We have two choices. We could turn it into a one form or a two form. At this point, we're just going to turn it into a one form. And then we're going to take d of it. Oh, that's exactly this calculation up here. And this is the thing we said, oh, it looks a lot like the curl. Well, we can make that precise now. This is exactly what you'd get if you took these three components, which are exactly the components of curl of a vector field, of the vector field f, and made a two form out of it. So in other words, we can take this and just put curl f there. So that's a more official way to say that the d, when implemented from 0 forms to 1 forms, encodes the gradient, and d, when it's implemented going from 1 forms to 2 forms, encodes the curl. And it's just using these nice notations to have a slick way to say turn it into a 1 form or turn it into a 2 form. Okay. So now let's just look at what we think d of a 2 form should be. Let's just look at this part first. D of a function times dy wedge dz. Well, dy wedge dz is definitely constant. If you look at the picture, like the flux tube picture of that, there's no variation at all. And so we can probably just pop that out to the right, and that's what we do. We just take d and we act on the function part, and we just pop the rest out. And we remember that secretly this was a wedge product all along, and this was too. It's just a 0 form wedge product, which is just regular scalar multiplication. Okay, so that's a start, but if we want to get it explicitly in terms of partials, we'd like to expand this out. Okay, so let's do that. Let's just put this. Oh, and I made a typo here. That should be R. That should Q and an R. Should change that in my students' papers. Okay, so this is going to be a Q and an R. They'll figure it out. Okay, so what is that going to be? Well, okay, I'm just going to copy it one more time. And here, I'm going to put in, I have a dp up here somewhere. Hey, there's dp right there. Okay, and I'll just paste that in. I love computers. Okay, and I have a dq up there. dq. Okay, oh, I should have copied the parentheses too. Not hard to do. And, let's put the plus signs here. Okay, and then plus, and then dr, I'm going to copy in the dr. So this copy and paste emphasizes the pattern, as it often does, that it's really, we only need to know d of a 1 form, and then the rest is algebra. And it's amazing that the algebra automatically produces the right combinations of things. Now this one is going to be surprisingly easy. You might think, ooh, this is going to be messy, even messier than the previous calculation. Not so. dy wedge dz, anytime you have the same 1 form appearing, it dies. Dy wedge dy is 0. Dz wedge dy wedge dz, well, we could always exchange the dz and dy, then they're next to each other, that's going to be 0. So in fact, you only get p sub x, oops, it's a capital P, p sub x times, let me just copy most of that in, times dx wedge dy wedge dz, plus, okay, then it's going to be qy, and it's going to be the dy wedge dx, dz wedge dx, okay, I'll put those on different lines, I guess, plus, and then rz, you know what I'm going to do? I'll be clever. There we go. That's what I should have done. I just delete everything else. Pow. Don't need the parentheses. Hey, that was cool. Okay, so now what about collecting it together? Remember, there's only really one 3 form. dx wedge dy wedge dz, these are all just plus or minus of each other. But a cool thing is that this is already in cyclic order. y, z, x, and this is already in cyclic order. z, x, y. So they actually are identical. And that's sometimes happens, doesn't always happen, but there are definitely, this is an example of a very important case where it does happen. So this is all just px plus qy plus rz times the standard 3 form, just the standard volume form, dx wedge dy wedge dc. And that should look familiar. If this were a vector field, remember we started out with a 2 form whose components were p, q, and r. But if this had been a vector field, this would be, pause and think about it if you don't want me to give away the answer, that would be the divergence. Okay. So a way to make that official is, let's assume we actually started with a vector field, then we did the star thing to turn it into a 2 form with exactly the same components, p, q, and r. So we're starting with f. We turn it into a 2 form using one of those 2 prescriptions. Then we d it, and we get just div f times the standard volume form. And if you think about it, that makes a lot of sense, because what do we usually do with a divergence? Like the way it comes into the divergence theorem, we integrate it over a region. So we actually want to promote it to a 3 form. And just like I was saying before, we don't actually integrate functions over 3-dimensional regions. What we should be integrating is a 3 form. So df star automatically gives you the function which we traditionally call div f, but attached to the 3 form, which it really kind of should be attached to anyway, because we're probably going to integrate it. Okay. And so this says that d going from 2 forms to 3 forms automatically implements the divergence. So this is a big payoff point where we see that the same exact operation, d in 3 different degrees, replicates div, grad, and curl all automatically. That's pretty neat. Okay. Now, next one. Actually, that's a good place to stop, and I'll come back in another video for the rest of these problems. You can take a look at them right now if you want.